Hello, I'm Ryan with High Desert Math Tutor, and today I want to talk to you about the two special right triangles. Now, these two triangles are essential to be very familiar with if you want to learn the unit circle or if you want to, be successful in studying trigonometry. And these two right triangles, they show up every day with buildings that we're around, with structures in rooms, in houses, on roads. And the big thing for us though is that it's very important that we remember the details of these two special right triangles so that you can go throughout trigonometry without using a calculator. These are essential for talking about what are called trig functions, trigonometric functions, without a calculator. So to begin, both of these triangles are set up so that the name of the triangles also includes the angles inside the triangle. So the first one is the 30, 60, 90 triangle. So you have a 90-degree angle, hence you have a right triangle. So in both of the triangles, we will have 90-degree angles. The question is, what are the other two angles? So the first special right triangle is the 30, 60, 90, and the side lengths. As this grows very nicely, the sides also grow nicely. 1, 2, square root of 3. Now, I'll go ahead and draw a triangle, then I want to talk a little bit more about these side lengths. So the 30, 60, 90 can be drawn in multiple orientations. So what I mean by orientations is this one's a little bit skinnier and taller, but I could have drawn this so that it is really more laying on its side. So inside this triangle, we have the smallest angle, the middle angle, and the largest angle. So the smallest angle is in the smallest corner. That's the 30 degrees. The biggest angle, the 90, is the right angle. So the 60 is the one in the middle in terms of size. And similarly over here, the smallest corner has the smallest angle, the thinnest corner. The middle corner has the middle angle, largest has the largest. Now, the same convention is true in these triangles as with any triangle. The smallest angle is always across from the smallest side of the triangle. So the largest angle is going to be across from the largest side. But my question to you is, which of these numbers, 1, 2, or square root of 3, which of these is actually the largest number? It's not obvious just looking at it here, but we can make it obvious. This is what math is all about. So what makes this not obvious is that there's a square root. Whenever there's something that's uncomfortable, unsettling, let's just get rid of it. So how do you get rid of a square root? You square it. But if we square one of these numbers, we're going to need to square all three of these numbers. So what we'll see is we have 1 squared, 2 squared, and square root of 3 squared. Well, 1 squared is just 1. 2 squared is just 4. And square root of 3 squared, what's nice here is that the square and the square root cancel, and we are just left with the number 3. So now I hope it's more obvious. Between the sides 1, 2, and square root of 3, the largest side is actually 2, or the largest number is 2. And we can see that when we square each of these. So this right here was just for you and I to help ourselves remind ourselves which of these is the largest if you forget. So across from the smallest angle is the smallest side, 1. Across from the largest angle, 90, is the largest side, that's 2. And the middle angle, middle side, square root of 3. Over here, same thing. Across from the smallest side is 1. or the smallest angle, we have the smallest side, which is 1. Across from the middle, or largest angle, is the largest side, 2. Then we have square root of 3. So I just want to remind you, these are the same right triangle. I just wanted to show you that it's pretty common to write this or draw it in multiple orientations. And I just want you to start thinking about that here. So this special right triangle, if you go back to your knowledge of similar triangles, you can make this thing grow or shrink however large or small you need it to be. And this is what makes special right triangles so convenient, is that if we can use these sides and these angles to put these triangles together, then we can just scale this thing up or scale it down, make it any size we need it to be. Now going on to the second special right triangle. So the name and angles, this special right triangle is the 45, 45, 90, and the side lengths are, notice, these are the same angle. Well, the sides are 1 and 1. And finally, the largest side is square root of 2. So both of these, I just want to point out before I forget, have very nice patterns with the angles and with the side lengths. 30, 60, 90, very easy numbers to count. 1, 2, square root of 3, also very easy numbers just to count up and to remember. Well, 45, 45, 90, two angles are the same. 1, 1, square root of 2. Two side lengths are the same. So there are nice little patterns that may make this easier for us to remember. So for the 45, 45, 90, we have a right triangle, and I will take this one a little bit faster. As you know, if you recall what I discussed here, is the smallest side is always across from the smallest angle. The largest side is always across from the largest angle. Well, these two angles are the same. We have two sides that are the same. So this should be a little bit easier for us to just throw in the 45-degree angle and the 45-degree angle, because both of those are the same. And we can throw on the 1 across from this one, and across from this one we have 1. And finally, our hypotenuse is the square root of 2. Okay, so we have our second special right triangle. Now, there's not much else to say in terms of, what these triangles are. We have the 45, 45, 90, the 30, 60, 90. But what you have to remember is that we want to remember these angles and these numbers so that we can put this triangle together. And then we can make this thing as large or as small as we need it by using scale factors and the whole concept of similar triangles. So that's a topic for another video. We already have videos on that already. But the one thing I want to point out is if you wanted to verify that these angles or these sides, I'm sorry, I did not sleep last night. If you want to verify that these sides do in fact work on a right triangle, or if you want to verify that these side lengths do work on a right triangle, how could we verify that? Well, you can verify that by using the Pythagorean theorem. Because just remember, the Pythagorean theorem has two sort of directions to how you can think about it. One direction is, say you have two sides of a right triangle and you want to find the third side. You can use the Pythagorean theorem to find that third side of a right triangle. But here, something that you may or may not have thought of is you can also use the Pythagorean theorem to verify if the triangle you have, if the side lengths that you have do in fact work on a right triangle. So I'll go ahead and just show you really fast here, and then we'll call it a day. But we'll use the Pythagorean theorem to verify these side lengths work as a right triangle. So the Pythagorean theorem says we take one leg, a squared, we square it. We take another leg, b, and we square it. That should be equal to the hypotenuse squared. And just recall, the hypotenuse is the longest side of a right triangle, and only right triangles have a hypotenuse. If you have a triangle that's not a right triangle, then the longest side is not called the hypotenuse. So here we have this Pythagorean theorem. So let's go ahead and fill this in. So we have the first leg squared plus the second leg squared. That should be equal to the hypotenuse squared. So here, what we can do is take the first leg, which is 1, the second leg, which is also 1, and the hypotenuse. We'll plug them into the formula. And now our question is, are these things equal? Are they the same? Is this the same as this? Well, 1 squared is just 1. 1 squared is just 1. And the square root of 2 squared, well, the square and the square root cancel, and we just get the number 2. And then 1 plus 1 is 2, and that is in fact equal to 2. So we have shown, using the Pythagorean theorem, that if we use these sides on a right triangle, or if we use these sides on a triangle, they do in fact work for a right triangle. So this part was just to help you understand how we can verify that these two special right triangles do in fact turn into right triangles with these side lengths. And also, this is just a fun fact of another way of using the Pythagorean theorem, which is to verify that specific side lengths do in fact work on a right triangle. But once again, we have only two special right triangles, the 30, 60, 90, the 45, 45, 90. For the 30, 60, 90, the side lengths grow very nicely. So we have 1, 2, square root of 3, and the angles, 30, 60, 90, they both grow in a nice progression. For the 45, 45, 90, the angles, 45, 45, 90, two of these are the same, one is bigger. Same for the side lengths, 1, 1, square root of 2. Two of these are the same, one of them is bigger. So I hope you kind of have a context of how to construct these triangles, how to verify that these are right triangles. And I hope that I got the point across that the purpose for these most often is we want to use these with trigonometry to get answers with trig functions without using calculators. And this is indispensable. You'll use this very often in trigonometry. You absolutely need to know this when you go into Calculus 1, Calculus 2, and just all math past that point. So anytime you need a refresher, feel free to come back and review the two special right triangles.